In this question, we are asked to show that the set S, which is a collection of all 2 times 2 symmetric matrices, is spanned by the matrices A1, A2, and A3. That means we have to show that the set S is equal to span A1, A2, A3. Recall that the set on the right hand side of the equation, span A1, A2, A3, is a collection of all linear combination of A1, A2, and A3. That means the set on the right hand side, span A1, A2, A3, is any element A in matrices of size 2 times 2, where A is a linear combination of A2 and A3. This is true for all A, B, C in R, for all scalars A, B, C, and R. Okay, and recall that to show that S is equal to span A1, A2, A3, we have to show 2 things. There are two statements that we have to show. The first statement is S is a subset of span of the set, and we have also proved that span A1, A2, A3 is a subset of S. So to complete the proof of this question, we have to prove statement 1 and statement 2. Right, so let us firstly prove that S is a subset of span A1, A2, and A3. It's supposed to be A3 in here. Right, so there is we start by letting A as an element in S. Okay, so since A is in S, and S is a collection of all symmetric matrices, therefore A is symmetric. Okay, and since A is symmetric, then the entries A2 and A3 should be equal. So we have A2 and A2. Okay, then we have to show that A here is also in. We aim to show that the matrix A here is also in span A1, A2, A3. Okay, to be in span A1, A2, A3, A must be a linear combination of A1, A2, and A3. That means we may write A as this. We can find scalars A, B, and C such that A is equal to this summation. Right, so we have to prove that the scalars A, B, and C exist. Okay, to show that we then substitute matrix A, A1, A2, and A3 as follows. And therefore we have A is equal to AC, CB. Comparing left hand side and right hand side of this equation, we found that A is A1, C is A2, and B is equal to A4. That means the scalars A, B, and C are exist. The scalars A, B, and C here exist, which is given by this equation. That means we have shown that A is a linear combination of A1, A2, and A3, and therefore A is in the set of span A1, A2, and A3, and therefore S is a subset of span A1, A2, and A3. So we move to the second equation, which is to show that span A1, A2, A3 is a subset of S. So we start by letting A is a matrix in this set. Okay, since A is in the set of span A1, A2, and A3, therefore A is a linear combination of A1, A2, and A3, and therefore A can be written as here. For some scalars A, B, and C, that means we assume that scalars A, B, and C exist such that A is equal to this summation. Alright, we have to show that A is an element of S. Okay, so A, we substitute matrix A with this A1, A2, and A3 as given by the question, and we end up to this matrix of A, where we can see here that the matrix A here is symmetric because the entries here are equal, which is equal to C. Therefore, A is symmetric, and therefore A is in S. So span A1, A2, A3 is a subset of S, and therefore span A1, A2, A3 is equal to S. We are given a vector space R4, where since the question does not mention the addition and scalar multiplication on R4, then we understood that the addition and scalar multiplication are the standard one. So we have standard operations on R4. Okay, and then we are given a set of 4 elements, and we are asked to determine whether the set is linearly independent or linearly dependent. So recall that the set S is linearly dependent, where S is the collection of R elements. It is linearly dependent if, whenever we write this equation, okay, the values of K1, K2 up to KR are not only 0, there are many other values for K1, K2 up to KR such that this equation is whole true. When that happens, the set S is linearly dependent. So we start our proving by write the equation. We write this equation where this is V1, this is V2, V3, and V4. This is the right hand side of this equation, and at the this is the left hand side. On the right hand side we have 0 vector. This is the 0 vector on R4 whenever we equip R4 with the standard addition and scalar multiplication. So this is the 0 vector, and to determine S is linearly dependent or linearly independent, we have to find possible values for K1, K2, K3, and K4. Possible values for K1, K2, K3, and K4. Are they all zeros, or there are any other values of K1, K2, K3, and K4? To do that, we look at this equation that we have just write down here, the start equation here. We simplify the left hand side, where we end up to the first component is K1 plus 2K2 plus K3 plus 2K4. Okay, and then the second component K1 minus K2 here minus K2 minus K3 and plus K4. We do the same for the third and fourth component, and they are all equal to zeros. Okay, and then we compare the left hand side to the right hand side, component by component, and we found that the first component here is equal to 0. The same goes to the second component. This is also equal to 0, and the third and fourth is also equal to 0. Therefore, we have this equation. This is from the first and the second component, the third component and fourth component. Remember that we are finding the possible values for K1, K2, K3 and K4. So, to get that, we solve the systems of linear equation, and we found that the systems of linear equation has infinitely many solutions. Whenever the system has infinitely many solutions, that means K1, K2, K3, K4 equal to 0 are not the only solution. They are not the only solution for the star equation. Therefore, it is linearly dependent. For B, we solve this question by using the help of theorem 3.7. 3.7 says that for a vector space Rn, for this vector space Rn, if we have S, a collection of R vectors in Rn, if R is greater than n, the value of R here is greater than n, then S is linearly dependent. That means if the number of element in S is greater than n, the dimension of Rn, then the set is linearly dependent. So here, our n is equal to 4 because R4, and the set S, here is the set S, has 1, 2, 3, 4, 5 elements. Therefore, R equal to 5. So, since 5 is greater than 4, which is R is equal than n, R is greater than n, then the set is linearly dependent. For C, we are going to use the help of theorem 3.6. It says that for any vector space, a finite set of vectors that contains the zero vector is linearly dependent. So first of all, we have to identify zero vector, the zero vector in the vector space. Here, the vector space that we are considering is R4, which standard addition and scalar multiplication. Therefore, the zero vector for R4 is 0, 0, 0, 0. And the set S that we are consider in this question is a set with 3 elements, and one of the element in the set S is the zero vector. Since it has the zero vector in the set, then from the theorem, the set is linearly dependent. In the last set, D, we are going to use the help of theorem 3.5. It says that whenever a set S with 2 or more vectors, the set S with 2 or more vectors, let me write as the set S contain V1, V2 up to V R, where R is greater or equal than 2, they are subset of a vector space V. S is linearly dependent if and only if there exists V, let's say Vj in S such that Vj is a linear combination of V1, V2 up to VR. We exclude Vj. Okay, so there exists one element in the set S such that the element is a linear combination of the rest of the element in the set. Okay, so here we have 5 is equal to 5. We have the vector here is equal to the linear combination of the rest of the element in the set. Okay, so since 5, 5, 5, 5 is a linear combination of 1, 1, 1, 1, therefore the set is linearly dependent. So it's supposed to be 5, 5, 5, 5 is a linear combination of the other elements in the set.